Hey guys, welcome back. It's Dr. D. We're talking about discrete probability distributions, and today we're going to talk about the last of the discrete distributions that we're going to be working with. It's called the hypergeometric distribution. And for the life of me, I looked around, I cannot figure out why it's called hypergeometric distribution because I'm not a mathematician. I'm just a guy who uses applied mathematics. I'm sure if you know why it's called hypergeometric distribution, I would love to know why. I'll tell my students. I do know how to work with it. I know how to explain it wellish, I hope. So what are we going to do today? Well, we're working with probability. And so for a while we've been talking about random experiments. And all of this is in the service of getting to, before I get ahead of myself, statistical inference, right? Learning how to make guesses. But not just any guesses. Guesses about the wider world based on the limited knowledge that we can get from looking at a sample of people that we have with us. So that's what we're working on, statistical inference. In order to do that, we need to add some tools to our toolkit. Probability is one of them. We have random experiments. These lead to outcomes. We assign these outcomes probabilities, and the probabilities all have to add to 1. We looked at a few ways to do this, to assign probabilities. The classical method is one. That's where we just divide probability evenly. Another one is the relative frequency method, where we just look at what's happened before and assign the relative frequencies. Another one is the subjective method, where we try to guess based on our best belief. And then in addition, we can model these things, and that's where we are today. We're modeling probabilities. And so today we're going to look at the hypergeometric distribution. I'm going to do an example later. Maybe I'll motivate this with an example. So let's just say that in order to do this, we work in quality control, okay? And we have eggs, cartons of eggs. We have 12 cartons of eggs. Again, this is more of a thought experiment. It's not going to produce that much of use right now because we're going to assume we know that 4 cartons contain multiple broken eggs. Okay. We know that 4 of these contain multiple broken eggs. We're going to spot check these. We don't have time to check every carton, so we check 3 cartons. We want to know what is the chance that exactly 1 will have multiple broken eggs. Huh. Okay, now this is similar to the binomial distribution, right, where we were doing a bunch of trials in a row. We tested, we did the same thing over and over again. But in this case, let's try to model this process the way we did when we did binomial distribution. Okay, so the way we would run this is first we inspect one carton of eggs. Let's call finding a carton with multiple broken eggs a success, just so that, and then no broken eggs, or not, less than or equal to 2 broken eggs would be failure. So we check that first one, and we might either succeed at finding a carton with broken eggs or fail. And then we check the second one, and again we might succeed or fail. And we check the third one, and we might succeed or fail. Here, we might succeed or fail. Going back to this alternate reality where we didn't find one first, we might succeed or fail here. In the third case here, we succeed or fail. And here we also succeed or fail. So we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. This is very similar in terms of the tree to what we did when we were looking at sales calls. In that case, again, the probability of success with the first one was 1/3. In this case, I'm not going to reduce it. I'm going to call it 4/12, right? When we first examine a carton of eggs, right, we pull out the first one off the rack. There's a 4 in 12 chance that that one will contain multiple broken eggs because 4 of them have multiple breaks, and there are 12 total. And so if we don't know, we close our eyes, we randomly select one. We might drop the eggs, but assuming we don't, there's a 4 out of 12 chance we'll find one with multiple breaks, an 8 out of 12 chance that we will fail to do so. The problem, and where this gets weirder, is next, right? Because in the sales calls example, when the person made a second call, there was also a 1/3 chance they would sell the magazine and a 2/3 chance that they would fail. In this case, that has ceased to be the case, right? If we have successfully found a carton with multiple breaks, then we know that we removed one of them that had it. That means that there are only 3 left that contain multiple breaks. And there are only 11 left to choose from. We're not going to put the first one back, right? And so the probability of finding multiple breaks on the second one is 3 out of 11. The probability of failing to do so is there's still 8 left that don't have multiple breaks, and so this probability down here is 8 out of 11. In the alternate reality where we didn't find multiple breaks in the first one, well, our probability of success here is still 4 out of, but now the denominator has changed. It's now 4 out of 11. And here, the probability of failing, well, now there's only 7 left that don't contain multiple breaks, so it's 7 out of 11. And so you can see that in every case, our probabilities have changed. The denominator is 11 every time, and the numerator is always add to 11 in whatever scenario we're in. But when we succeed the first time, it changes the numerator in the success of the second trial. When we fail the first time, it changes the numerator of failing in the second trial. And so this is the problem. The problem here is that trials affect future trials when we draw without replacement. Now, this is not a perfect model, or maybe the binomial one wasn't a perfect model, because I worked in telemarketing and I would model that as a binomial experiment, but that was without replacement as well, right? They would never give me the same exact person 2 times in a row. I think it was probably built into the code to make it physically impossible to do so, right? So, what's wrong? Well, let's imagine that instead of having 12 cartons of eggs, we have 12 million cartons of eggs, and 4 million of them contain multiple breaks. Well, now, if we find a success, the first one, then that leads to new probabilities of 3,999,999 divided by 11,999,999, which is not appreciably different from 1/3, right? Failure now would still be 8 million out of 11,999,999. And that's when we succeeded on the first trial. If we failed on the first trial, they'll be different, but it's not so different. And so another way to think about this is when we're doing binomial trials, binomial experiments with small populations, right? That's really what we're doing here. Small enough that each trial can affect future trials in a way that matters, right? I don't think this matters. Failing in one does not really fundamentally change what's left, because just the population is so large. In this case, the population is 12, and that's not so big. Okay, now when we want to account for the population, we need to know about the population. We need to know some things. So before, when we dealt with binomial trials, we had a few variables, and we're going to have those same variables, right? X now, as before, is still going to be the number of successes, and N is still going to be the number of trials. And I highly recommend you go back and watch the binomial one, because the discussion here and the discussion there are related, right? It will help you understand both, I think, if you understand. It will help you understand each if you understand both. In this case now, though, we need the size of the population. Generally, we call that big N. So this is the size of the population. And we also are going to need to know the underlying probability. The way we can take care of that is by assigning the variable R to the number of successes in the population. And so I'm going to slightly modify the variables I just defined a minute ago, X and N, because I don't want these to be unclear. This is the number of successes we observe, and this is the number of trials we observe, because it's not the number of successes. There's 2 numbers of successes. One is the number that we observe, and one is the number of trials. As before, one thing we noted is that if we do these trials and we get X successes, that implies that we will have N minus X failures we observe. Right? So that's what that is going to be. And if N is the size of the population, and R is the number of successes in the population, curly brace, big N minus little r is the number of failures in the population. All right, so how does this work? Well, now we have all of these variables, and I'm going to outline the hypergeometric probability distribution, and then we're gonna play with it a little bit. What we want to know from this question above is a bunch of things, right? We can assign these values. We wanted to know the probability that one and only one carton would have multiple breaks. We know that we're going to look at 3 cartons. We know that there are 12 cartons in total, and we know that 4 of them contain multiple breaks in total. Right? So these are our parameters. This implies that there are n minus x2 failures we want to observe, and big N minus r, 12 minus 4, 8 failures in the population. So these are all the values we want. Once we know these things, what we want to know then is the probability of observing a given value of x. And so we're going to have a probability distribution function. X spits out another number, or f spits out another number when we give it an x. This is going to be a probability, so that 0 is going to be less than or equal to f of x, which is going to be less than or equal to 1 in every case. And this is that probability distribution. We call it the hypergeometric distribution, probability mass function, whatever you want to call it. F of x equals, okay, the denominator is the number of different ways that we can select a number of combinations of n different elements from a population of big N. Okay, so these are the number of different paths in a tree. You can kind of, I guess it's combinations, so the number of different possible outcomes. And then the numerator is going to be, well, we need r successes, or out of the r successes we need to choose x of them. And out of the n minus r failures, we need to choose little n minus x of those. So it's the product of these divided by that factorial. All right, so this is a discrete distribution, as before. X, right? We can have 0 successes, 1 success, 2 successes, all the way up to little n. Although we should be careful because it may be the case that r is less than n. If r is less than n, then f of x is 0 for x greater than r. Right. Cool? Cool. Okay, so let's look at this case with eggs. What is the probability of finding one egg or one carton with multiple breaks? Let's plug these values in. Pick a color here. F of x in this scenario, well, that's going to be, we know that there are 4 successes. We want to choose one of those. We know that there are 12 minus 4 failures, and we want to choose 3 minus one of those. And then out of 12, we want to choose 2 successes. Or I'm sorry, out of 12 we're choosing 3, not successes, 3 trials. All right, let's do some math here. These are, remember, if you remember, when we have, let's do P and Q. This notation, P choose Q, is equal to P factorial over Q factorial times P minus Q, the quantity factorial. And that's just what this notation means. And so we're going to have to find that out. And the way to think about this is a number of ways there are to get Q successes and P trials. Right? That's one way to think of this. And so there are going to be some shortcuts that will come in handy. Maybe let me outline those shortcuts for you first over here. Let's say that we have 3 trials and we want to know how many ways there are to get 0 successes. Well, it turns out that there's only one. Fail, 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 right? That's the only way to get, that's the only path that will lead you to 0 successes in 3 trials. And so this is equal to 1. If we have 12 trials, we want 0 successes. Again, fail, 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 fail. There's only one way. You have to do that, right? And so if we know that we have Q different trials, and we're choosing 0, that's always going to be Q. So that's a shortcut. In addition, if we have 12 trials and we need 12 successes, you need to succeed, 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 etc. all the way to all of them, which means that there's only one possibility here. 3 trials, choose 3 successes, succeed, succeed, succeed. There's only one possible way here. And so Q, choose Q, also equals 1. So both, sorry, this isn't Q, this is 1. I wrote that incorrectly. That's 1. So Q choose 0 or Q choose Q are both 1. Two other shortcuts that will come in handy. What if we have 3 trials and we want to choose 1 for success? Well, we can get success in the first one, or success on the second one, or success on the third one, right? So we could do succeed, fail, 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 succeed, fail, or fail, fail, succeed. So there are 3 ways to get 1 success, right? How about if we did 6 and we wanted 1 success? Well, then we could succeed first, fail in the next 5, fail on all of them except the second one, fail on all of them except the third one, and so on and so forth. So if we want 1 success, in this case, there are 6 possible ways to do it. In general, if we have Q trials, we want 1 success, there are going to be Q different ways to do it. That's why I messed that up here, is that is one of them. Alternatively, if we want to choose 2 successes out of 3, that's the same as choosing 1 failure. And again, there are 3 places to put the failure. We can fail in the first trial, or on the second trial, or on the third trial. Those are the only 3 ways we can fail. Only 3 places we can put that failure. So this will also be 1. Similarly, if we want 5 successes in 6 trials, we can fail the first time and succeed the other 5, fail the second time and succeed all the rest, fail the third time and succeed all the rest. So this also equals 6. In general, if you have Q trials and you want Q minus 1 successes, then this is there are Q different ways to do that. So those are the only shortcuts I know of. This one, this one, this one, this one. But we will take advantage of those. It shortens the math a little bit. Okay, so here we have 4 choose 1. By our shortcut before, we just established that this is 4. Times 12 minus 4 is 8. Choose 2. I'm going to have to expand this one out. And 12 choose 3. I'm going to expand that a little bit now. I'm at least going to expand, yeah, I'll just expand it all the way. 3 factorial on the bottom, 12 minus 3, the quantity factorial, and 12 factorial is in the numerator. Okay. This turns into 4 times 8 factorial divided by 2 factorial times 8 minus 2, the quantity factorial, all over. The way I like to do these, again, is to solve for the bottom first, and then to expand the top one only as far as I need to. 12 times 11 times 10 times 9 factorial. And those 9s will cancel out here. Alright, scrolling down. We now have 4 times, again expanding this, 2 factorial times 6 factorial, 8 times 7 times 6 factorial, all over 12 times 11 times 10, divided by 3 times 2 times 1, equals, canceling out, we have these 6 factorials cancel out, 4 times, 8 times 7 is 56, 2 factorial is 2 times 1, so that's 2. All over 12 times 11 times 10. 12 times 11 is 132. And then multiplying that by 10, we get 1320. So adding the 0 there. And then 3 times 2 times 1 is 6 times 1 is 6. So 4 times 56 divided by 2, that's going to be 2 times 56, which is 112. 112. All over. 1320 divided by 6 is 220. There we go. So 112 divided by 220. That's going to be 50%-ish. You can tell because 110 is half of 220. 112 is a little bit more. And sure enough, if you pop that in your calculator, you should get 509. The 09 are continuing. All right. So that's the answer to the question we had before, right? What's the probability that we'll get 1 carton with multiple breaks out of 3 trials if 4 out of 12 contain multiple breaks, right? This formula does it for you. And I said f of x here, but this is really f of 1. All right. What else? What about 2 cartons with multiple breaks? Let's try 2 cartons just so we can look at that again. I'm going to try not to do any math twice if I don't have to, just so you know. So if you see me skipping steps, it's because I did it in earlier, and you can rewind to try to see that. In this case, there are 4 successes in the population. I need to get 2 of them. And there are 8 failures, 12 minus 4, we already did that, and I need to get 1 of those, but I didn't subtract this yet, so we'll call it 3 minus 2. This bottom here is going to be 12 choose 3, and I already know that, so I don't have to write that, work that all the way out again, right? This worked its way to here, over to here, over to here, over to here, over to here, and that turned into 220. So that's the denominator. 4 choose 2 is going to be, switching colors, 4 factorial divided by 2 factorial times 4 minus 2, the quantity factorial, that's a 4. My tablet joined it for some reason. Times 8 choose 1. And we learned a shortcut about that just a minute ago. 220 is again the denominator. Now I have 4. I'm going to expand the bottom first. 2 factorial times 2 factorial. 4 times 3 times 2 factorial is the numerator. Times 8. Canceling things out here. 2 factorials cancel out. This gives me 4 times 3. 4 times 3 is 12. Divided by 2 times 8. All over 220. Which is equal to 6 times 8 over 220. Which is equal to 48 over 220. And 48 over 220 is about 22%. 0.218. The 1 8 are continuing. So there you go. That's how we use the hypergeometric function. You could do the probabilities for f of 0 and f of 3 as well. Those will go pretty fast. But I'm not going to do those right now. Hypergeometric. So what else do I want to tell you? Well, it's similar to the binomial, right? And so when we talk about expected value and variance, when we did, let's do expected value for binomial, right? The expected value for binomial was mu equals n times p. For hypergeometric, it's exactly the same, except we don't have p, right? Instead of p, we have the probability of success, which is just the proportion in the population, r divided by big N, right? Which is the same as p. It's just expanded because we care about the actual population size now, where we didn't care about that before. It's countable. Before it was just infinitely large. Similarly, the variance of x for binomial, sigma squared, was n times p times 1 minus p. I'm showing you this because it looks very different with hypergeometric. If you just saw it, you wouldn't necessarily make the connection, but I want to show it to you. So it's going to be very similar. It's not quite exactly the same now. We have n times r over n, which is the same as mu, just like it is with binomial, times 1 minus r over n, that quantity. And this would be exactly the same as the binomial, but because we're drawing from a finite population, we need to add a correction factor. So we multiply by big N minus little n over big N minus 1. And it's useful to think about this for just a second, right? This big N minus little n, this n is always going to be greater than or equal to 1, right? What this means is that the top is always going to be bigger, and the bottom is always going to be smaller. And they're always both going to be positive, which means that this falls between 0 and 1. Right? So, this accounts for the fact that this reduces the variance to some extent because the population is not so large. And so this thing right here is called the finite population correction factor. And it just accounts for the fact that when we draw from the variance that we're pulling things actually out of a finite population. As little n gets big, this top gets smaller. As big N gets really big, this approaches 1, right? So as big N gets large, as the population gets big, this approaches the variance of the binomial distribution in the limit. And this is actually just straight up equal. So there you go. That's the hypergeometric distribution. It has a lot of applications. One of the most famous and popular is poker hands, and I'm probably going to make a video about poker hands soon to kind of demonstrate that. But hypergeometric is really useful whenever we draw without replacement. Similar to the binomial, but we just have a small population. Cool. Thank you guys very much. I hope that you found this useful. Again, I'm Dr. D. If you have any questions or comments, I always appreciate feedback. Please let me know in the what are they? John Green calls it the doobly-doo. There you go, in the doobly-doo. Or no, I guess it's the comments thread. I don't put anything in the doobly-doo except what I did. But yeah, put your comments below. And if you have any yeah, or you can just email me if you're interested in more stuff. If there's something you particularly want to see, I'm starting to solicit requests for videos. So if I'm closing in on the end of all the videos that I would like to make that right now, and so if there's something you want to see, let me know, and I may take you up on it. Thanks, guys. See you next time.